Hello everyone, welcome to this video looking at how to find volumes using cylindrical shells. So we already saw a little bit how to find volumes in the last section, where the idea was to look at cross sections, find the areas of the cross sections, and then integrate. But we need one more method because sometimes the cross sections can be tricky to find. So before we start thinking about cylindrical shells, let's see why there's a need for this method. So what is the motivation? So suppose we have the standard problem of when we want to rotate a region around an axis, but let's suppose we want to rotate a region around the y-axis. So we want to rotate around the y-axis. How did we do that? Well, then we looked at the simplest cross sections. So the simplest cross sections were those which were perpendicular to the y-axis, and then they were either circles or washes. So how did we find the area of those sections? We had to find the inner radius and the outer radius, or just the radius if they were circles. And the radii corresponded to x values, right? That was the distance from the region to the y-axis, so they were x values. So we had to solve to find the x values of the curves in terms of y. So that's a bit of an algebraic step that we might or might not be able to do. It depends on how complicated the formula is. So there was a slight problem. Okay, and then once we did that, we found the area A of y and we integrated with respect to y. So that gave us the volume. So the question is now, what if we can't solve for these radii x in terms of y? Suppose we had some curve, y equals f of x, and it's a pretty complicated equation or not something that we can easily solve to put back x in terms of y. What should we do? In that case, we need another method. So that's going to be the method of cylindrical shells. So let's see how it works. So before we get on to looking at cylindrical shells, let's look at a kind of example, which is a computation we're going to need. What is a cylindrical shell? So a cylindrical shell is just a big cylinder with a small cylinder removed with the same height, but a smaller radius. So let's take a cylindrical shell, has height h, an inner radius r1 and outer radius r2. So here it is on a picture. We take a cylinder and we remove a smaller cylinder from the inside. The heights of the cylinders are the same, but the radii of the cylinders are different. So the inner radius is R1, the outer radius is R2. There is this thickness, which is the difference between the radii, right? If we take a big cylinder and we remove the middle piece, the thickness is what is left. The delta R is going to be R2 minus R1. Okay, how do we find its volume? Well, we could just do the volume of the big cylinder minus the volume of the small cylinder. Okay, but there's going to be a helpful way to write that. So I'm going to skip the algebra. But let's say R is R1 plus R2 divided by 2. So R is the average radius. So it's the average of the inner and outer radius. And delta R equals R2 minus R1. That's the thickness that we just talked about. Okay, then with simple algebra, you can show, if you do pi R squared pi R2 squared H minus pi R1 squared H, you rearrange, you use R and delta R, you can write the volume as 2 pi R times H times delta R. So we can say the volume of a cylindrical shell is 2 pi times the radius, so that's the circumference, times the height, times the thickness. So we're going to keep this formula in mind later because we're going to approximate volumes of regions by volumes of cylindrical shells. So now we can calculate volume of cylindrical shell pretty easily. It's just the circumference going around times the height times the thickness. So now that we can calculate volumes of cylindrical shells, let's see how to approximate more general regions. So let's suppose we have a solid, which is, say it's the area underneath the graph of y equals f of x from x equals a to x equals b. So bounded by the curve in y equals 0 from a to b. And let's say we rotate it around the y-axis. So if we were to do slices, we'd have to solve for x in terms of y. That might not be possible, but let's see a different method. So the strategy is going to be, as usual, we want to approximate by simpler things. So we divide AB up into lots of little pieces, xi minus 1 to xi. As usual, they have the width delta x is b minus a over n. And then we let xi bar be the midpoint of xi minus 1 to xi. So xi minus 1 to xi are our little intervals, and then we take the midpoints. And we're going to approximate each little subinterval by a rectangle, as usual. And the sample point is going to be the midpoint. So the rectangle is going to have height f of xi bar and width delta x. And then rather than rotate the solid around in that piece, we're going to instead rotate the rectangle. And that's going to be a pretty good approximation of the solid, right? The rectangle approximates the region of the graph in that area, in that region. So if we rotate the rectangle, that's going to give us a reasonable approximation of the rotation of the area under the curve. So if we rotate this rectangle, then we're going to get a cylindrical shell. It's going to have average radius xi bar, it's going to have height f of xi bar, and it's going to have thickness delta x. So let's see how that works. So we're saying, approximate the graph by rectangles. If we rotate the rectangles, we get cylindrical shells, and the cylindrical shells put together are going to approximate the volume that we're after, the volume of revolution. So here it is on a picture. So let's start with the top picture. So here we have the graph of some function. We're looking at the region underneath the graph above the x-axis from x equals a to x equals b. And we're going to rotate this around the y-axis. And we're saying we should break it up into little bits, and then on each subinterval, xi minus 1 to xi, we approximate by a rectangle. So here is our rectangle. And then rather than thinking about rotating all the graph at once, let's just think about what happens when we rotate this little rectangle, and then we'll put it all together. So if we rotate all this this rectangle, we get a cylindrical shell, right? The included piece is the rectangle, so we're not including everything between the y-axis and the start of the rectangle, but we are including then the piece between the x-axis up to the end of the rectangle. So we have this little thin strip, we're rotating it around, we're going to get a cylindrical shell. So what are the dimensions of the cylindrical shell? Okay, the height is the y value, so that's going to be f of xi bar. The thickness is the length of this little interval, so it's going to be delta x. And then the average radius is going to be the midpoint of xi minus 1 and xi, right? The radii are the distance to where we're revolving. So the inner radius is xi minus 1, the outer radius is xi, the average radius is xi bar. So now we know the height, we know the thickness, and we know the average radius. And we said that the volume of a cylindrical shell is the circumference, which we have, that's 2 pi times xi bar, times the height, which is f of xi bar times delta x. So we managed to find the volume of this little cylindrical shell. And now we play the same play the same game as usual, right? We can approximate the volume of the of the area of the region of revolution. If we revolve this entire area around the axis, we get a shape in 3D. We can approximate it by putting together all of these little cylindrical shells. So we can add all these together to get an approximation of the volume we're after. And then as usual, it's an approximation. How do we get better and better approximations? Well, we approximate finer and finer. And in the end, if we take the limit, we get the true volume. Okay, so that brings us to the volume formula for using cylindrical shells. So if we want to find a volume of a solid, where we rotate about the y-axis, the region under y equals f of x, and above the x-axis, so above y equals 0, from x equals a to x equals b, as in the pictures, that's just the integral from a to b of 2 pi x times f of x dx. And as it's taken, you could use this formula on lots of examples and figure out how to make it work. So this is a useful formula. But also we're going to use this in other settings, say where things vary. So for instance, here we're looking at the region underneath a curve. We might look at the region between two curves. Or here we're rotating about the y-axis, but we might be rotating about the x-axis or about a line which is parallel to the one of the axes. So rather than just remembering the formula, because we're going to use it in a bunch of different settings, I think it makes sense or I think it's really useful to remember why it works. So we're approximating by little shells, and then we're integrating the volume of the little shells, right? So here, a typical shell, it had circumference 2 pi x, because the average radius was x. It had height f of x and thickness dx. We multiply the circumference, the height, and the thickness of the shell to get the volume of the little shell, and then we integrate those to get the volume of the solid. So let's see how that works on one example, and then in the next video, we'll look at some more complicated examples where we mix things up a little bit. So here is a pretty model example. So we're finding the volume of the solid by rotating about the y-axis, the region under the curve or bounded by the curve, y equals 2x squared minus x cubed, and y equals 0. So since we're not specified any x values, we should try to figure those out by figuring out where our regions intersect. Right, so we can see this is a curve. It starts at the origin, and when x equals 2, it passes through y equals 0. So y equals 0, which is the x-axis, and our curve intersect at x equals 0 and x equals 2. So we know the limits for our shape. And then we have to figure out what the shell looks like. So how to figure out the shell? Well, at x, we're approximating by a rectangle. And let's say this rectangle has thickness delta x. So this is going to be the thickness of the rectangle. And then the average radius is going to be the distance from x to the line where we're revolving. So in this case, we're revolving around the y-axis. So the distance from x to the y-axis is the radius. The radius in this case is going to be x. And then finally, the height of the shell is going to be the height of the rectangle. So that's 2x squared minus x cubed. And you can imagine that as you rotate this rectangle, forgetting the rest of the shape, as we rotate this rectangle, we're going to get a cylindrical shell, right? We look at revolving this far line, that gives us a cylinder. And if we revolve the small line, the closer line, we get another cylinder. And then we have to take the difference of the two and take what's left over because we're only interested in the rectangle. So if we revolve this rectangle around, we get this cylindrical shell. Okay, and we just said it has circumference 2 pi x, where x is the radius. It has height 2x squared minus x cubed, right? That's the y value. And it has thickness dx. So we multiply those together, we get the volume. So we have 2 pi x times 2x squared minus x cubed dx. And then finally, we just integrate the volumes of the little shells. So where do our shells start? They start when x equals 0, and our shells end when x equals 2. So we have to integrate from 0 to 2. Okay, we can do that. We bring out the 2 pi, which is a constant. We multiply through by x, so we're going to get 2x cubed minus x to the 4. Now it's just an easy fundamental theorem of calculus question, right? We find the antiderivative, we plug in 2, we plug in 0. We subtract, we simplify. In the end, you'll get 16 pi divided by 5. Okay, so just to summarize, we said if we want to work y in terms of x, and we want to revolve around the y-axis, then we can do that using shells. And the strategy we have to do is to integrate the volume of little shells. And the volume of a little shell is the circumference times the thickness times the height. So we have to draw a little rectangle, think about what shell we're going to look like when we revolve around the axis, find the circumference, find the height, find the thickness, multiply them to get the volume, and then integrate to get the overall volume. And this was useful when we could not use sections. For instance, if we have y in terms of x and we can't get x in terms of y, and we want to revolve around the y-axis, then we have to use shells. Okay, thanks everyone. See you next time.